Okay, everybody, so we are starting at the bottom of page 5. And what we were talking about was wholes and how these come from restrictions on the denominator, just like asymptotes. So, folks, if I look at this function and I look at the denominator, what restricted value do we have on x? X cannot be -1. Now, that could either be a vertical asymptote at -1, or it might be a hole at -1. Now, I want to show you what happens if we actually plug -1 into this equation. So if I plug that in, we would get -1 plus 2, -1 plus 1, all over -1 plus 1. -1 plus 2 is 1. -1 plus 1 is 0. All over 0. So, folks, I get 0 over 0. Now, usually, any number over itself, whether it's 4 over 4, 0.5 over 0.5, a third over a third, what do those normally equal?
0.
1. So, any number over itself equals 1, except for 0 equals 0. 0 over 0. This does not equal 1. So this is still undefined. Which is why it doesn't actually cancel out, even though we're kind of going to fudge that to figure out there's a hole there. So I want you to write it's still undefined, so it doesn't actually cancel. Which is why we say it quote unquote cancels. So what we mean by canceling is everything that we've been doing in this chapter so far. If I have within a fraction the same factor over itself, up till this point we've been like, yeah, go ahead and cancel that out. When we are simplifying, it's all fine. But when we're thinking about x as an input and things that we can and cannot plug in here, if I'm trying to graph something on a coordinate plane, I'm not going to have a domain of all real numbers because that -1 is restricted. So we are going to say it cancels. And when a restriction cancels, we say that it is a hole instead of a vertical asymptote. So a hole is a restriction whose factor cancels. And what's interesting about this is the graph actually ends up looking or behaving like whatever is left. So this graph would look like y equals x plus 2, or it would look like a line with a hole at -1. So I'm going to go ahead and just sketch what this looks like. Y equals x plus 2 would be a line with a y-intercept of 2 and a slope of 1. Up 1, over 1. Now, if I do down 1, back 1, that takes me to this restricted x value, where I have this open dot or hole. Down 1, back 1 were defined, down 1, back 1 were defined. So that is what my graph actually looks like. So the restriction, quote unquote, cancels, and we're left with whatever is left on the top. That's how our function is behaving. Now here's where I want to show you the limitations of your calculator. If I type that original equation in, x plus 2 times x plus 1, all divided by x plus 1. Let's change my zoom. Does it look like we have a hole or a break in our function? No. So this is one of the reasons why being able to find these key features algebraically is so important, because your calculator is like, line, but what our algebra shows us is, no, we actually can't plug in that value of -1. Now, if I hit trace, and I type -1, just like we did with P over Q values, with testing things on the graph, notice what happens at -1. What are we seeing? Nothing. It's like, nope, we're not actually getting a y value there. So you can use trace to verify that there is a hole. So let's go ahead and write that. Use trace to verify the hole. But it's really tough to tell that there is one there just based on the graph or where there's one. You wouldn't just want to look at that line and start plugging in random x's and being like, are any of these undefined? So this is why we are going to use a combination of our calculator and algebra strategies to figure out where these key features are. Woof. So what have we got so far? Horizontal asymptotes. Top heavy, bottom heavy, same. And again, you will get this list of rules. We've got vertical asymptotes and holes. Both of these come from restrictions on x, which come from our denominator. So let's go ahead and turn the page. And let's start looking at these key features relative to these two graphs. So looking at this first one, do we have any restrictions on x? What's the one thing that x can't be that would make this fraction undefined?
5.
It can't be 5. Now, as I'm looking at this, can my factor that gives me 5 cancel? Nope. So it can't cancel, so it's a vertical asymptote instead of a hole at that value. So we would have a vertical asymptote at x equals 5. So it can't be equal to 5 is the restriction, but it's equal to 5 because that is the location of our asymptote. And what's nice is, since we know that this restriction is a vertical asymptote and not a hole, we know we're not going to have any holes at all. So you can go ahead and write NA or draw a line or color it in or leave a blank showing that there won't be any holes for that function. So let's go ahead and add this key feature onto our graph. A vertical line that goes through tick mark 5. Also a dashed line. Let's go ahead and look at our next one. What restrictions do we have on x on the next one? Can't be -4. Will that cancel or not? Nope. So can't cancel. So we're stuck with that restriction as a vertical asymptote. So a vertical asymptote at x equals -4. Go ahead and draw in that vertical line on your graph. On your own, see if you can, maybe not on your own. Folks, why did I change my mind about this one? What do you think is different? The x squared. What do you think we should do first before we determine what restrictions we have? We should probably try to factor this. So let's go ahead and try to factor this. See, a product of -2 and a sum of -1. That would be x minus 2 and x plus 1. And then, can I factor x squared minus 9? Yes, indeedy. We've got x plus 3 and x minus 3. Difference of squares. So what are my restrictions for this one? There are 2 restrictions on x because there are 2 values that would make this denominator equal to 0. X cannot be -3 or +3. Can I cancel out either of those restriction factors? Nope. So these are both going to be vertical asymptotes. So vertical asymptotes at x equals -3 and x equals +3. So -3. Vertical line there. +3. Vertical line there. So now we know that there won't be any holes for that one, and we have kind of some quadrants that we know our graph pieces are going to exist on. What we don't have at all so far are any exact points. Now if you're like, well, let's just make an input-output table. Do we really want to do an input-output table and plug in x values for this? Not really. Kind of a lot of work, and these are fractional functions, so we're going to end up with some, kind of nasty fractional points. So this is what brings us to the next part. Go ahead and flip back to page 6. And we're going to talk about the y-intercept and the zeros. The zeros are a number and 0, or your x-intercept. Whereas your y-intercept is 0 and a number. Now, you may recall back when we did linear functions, we had the cover-up method. There's not really the cover-up method here. It's just going to be a matter of plugging in and solving for that variable. Now, if it helps you, f of x is the same as what? Y. So if you want to put y equals there instead of f of x equals, you certainly can. So what we are going to do is plug in 0 for one of the variables to find the corresponding coordinate. So for the y-intercept, we're going to plug in 0 for what variable? And for the x. So we'll have 3 over, actually I should put the y equals first, scratch that. We're going to have y equals 3 over 0 minus 5. So the y-intercept is always 0 and a number. So we are plugging in 0 for x. And now we're going to simplify it to figure out the y value. 0 minus 5 is -5. What's 3 over -5? It's just -3/5. So as a coordinate, our y-intercept would be 0, -3/5. And that's going to be our first exact point on our graph. So here's 0, here's -1, so -3/5 is going to be just a titch over halfway. So there's our y-intercept. Now what's nice about this is it shows me what's going to happen in this quadrant. We know that we are going to probably be curving up this way towards the asymptote going to the left and curving that way towards the asymptote going to the right. Now the nice thing is we'll be able to check ourselves using our calculator, but now we at least have one exact point to go off of. Same thing we are going to do with our x-intercept. We are now going to take 0 and plug it in for the y value. So if I plug in 0 for y, this gives me 3 over x minus 5. Now, if I were you, I'd be looking at that going, I don't really know how to isolate that x, Ms. Cairo. Well, we just did something similar to this on the homework quiz today. Folks, what drives this problem is, ew, a fraction. Let's get rid of it by multiplying by what? We can multiply both sides by x minus 5. And what does that do for me? Well, goodbye x minus 5 over meow. And what is 0 times x minus 5? That's going to be 0. So, all right, the x is gone and 0 equals 3. We didn't get a value for x. We just got this very clearly false statement. What do you think that tells me about my x-intercepts? There aren't any.
How is that very clearly false statement?
Because 0 does not equal 3. So we're not saying x equals 3 or x equals 0. So I don't have a variable left at all. So 0 equals 3, a constant equaling a different constant. That's how we know that we've gotten a false statement or no solution for that one. So there are not going to be any x-intercepts. So key feature-wise, here is what we have gathered. We've got a y-intercept. We've got no x-intercepts. We've got a vertical asymptote at x equals 5. And a horizontal asymptote at y equals 0. And that brings us to this lovely graph. Now we are going to use our calculator to supplement the rest of what this will look like. Now when I type this in on my calculator, it's very, very important that you trap any binomials or trinomials in parentheses. So I want everybody to go ahead and try this now. Let's make sure we can get our graph working. So I'm going to clear out any junk that's in my y equals, and 3 divided by x minus 5. Trapping that binomial in parentheses. And here we can see the swooshes of our graph. So I can, from that exact y-intercept, curve up to that asymptote and curve down towards this other asymptote, making sure we put arrows on both ends of that. This one, this right swoosh, we don't have any exact points for, so best you can just try to make it look like your calculator graph. Just swoosh on through, making sure that you don't cross the asymptotes. So folks, I want to show you what happens if we didn't put parentheses there. Does that look like the same graph? Nope. Anybody else's calculator being weird? So the parentheses are important. I'm going to go ahead and clear out that gross one in there. And what's nice is we can kind of verify some of these key features. Folks, if I trace x equals 0, what am I going to see? What happens if I plug in 0? We get negative 0.6, which is what negative 3/5 is equal to. I can also plug in 5 because I'm doing my x stuff. If I plug in 5, what should I get? Nothing. There is a vertical asymptote there. That's one of our restricted values. And so we can see, yep, our function is not defined there. Okay, let's go ahead and take a look at the next one. Hoping we forgot to cross off that there wouldn't be any holes here. So every restriction you have on x will either be a vertical asymptote or a hole. It cannot be both. Let's go ahead and find the y-intercept for this function. So we're going to take 0 and we are going to plug it in for x in our function. So y equals, or f of x equals, 2 times 0 over 0 plus 4. Where's our y-intercept? What's 2 times 0? 0! So I get 0 over 4, which is just 0. So my y-intercept is at 0, 0. Or the origin. So let's go ahead and plot that exact point on my coordinate plane. So 0, 0, plunk. A nice exact point.
How'd you get 0, 0?
Because we take 0 and we plug it in for x. 2 times 0 is 0. 0 plus 4 is 4. 0 divided by 4 is 0.
Oh, this is all one problem.
Huh? Oh no, this was one graph. This was the other graph. So now we're using this equation. So now what about the x-intercept? For the x-intercept, we're going to plug 0 in for y. So 0 equals 2x over x plus 4. How will we solve this for x? Multiply by x plus 4 to get rid of the fraction. And what's 0 times x plus 4? Still 0 on the left. And on the right, we have 2x. So what does x equal?
2.
Divide both sides by 2.
X equals
X equals 0. So are we surprised that 0, 0 is also the x-intercept? Nope, because the origin is both an x-intercept and a y-intercept. It is exactly where the x and the y-axis are intersecting. So, neat. There's our exact point. We are now ready to use our calculator to get an idea of where the swooshes are. So, y equals 2x divided by parentheses x plus 4. So you got to have those parentheses. So y equals 2x over x plus 4. And there's what our graph looks like. So what we want to do is make sure we swoosh through that one exact point that we have. So from there, curving down towards that asymptote, curving up towards that asymptote, and then up in this quadrant, we're just going to sketch it curving up to that one and down to that one. But we need to make sure that we have arrows on both sides, on both ends of each of those swooshes. If I hit trace and 0, what should I get? 0. Woo! What happens if I trace -4? Nothing. It's undefined there because of the vertical asymptote. Riveting. All right, folks, turn the page. I want you to see if you can find the x-intercept and the y-intercept for this one. Y-intercept, remember, is 0 and a number. X-intercept is a number and 0. It's a bit more complicated because there's a few different places to plug in that 0. Zero squared, 0. Minus 0, 0. Minus 2, -2. On the top, 0 squared is 0. Minus 9 is -9. Okay, are we going to leave that as -2 over -9? No, make them a plus. And our y-intercept is 0, 2 ninths. You can look and see what that decimal is on your calculator if you want, but I know that it's less than 1/2. So 0. And then up a titch. Right about there-ish. Now for the zeros. AKA the x-intercepts. So when I go to plug in 0 for y, 0 equals, I'm going to go ahead and use factored form here. X minus 2, x plus 1, all over x plus 3, x minus 3. And I'll explain in a minute why factored form works a little bit better for doing the zeros. So what am I going to multiply by to get rid of that denominator? X plus 3 and x minus 3. I'm going to be lazy and just write denom. I'm just going to multiply through by the denominator, which will give me 0. I'm going to sidebar down here. 0 equals x minus 2 and x plus 1. How do we solve something like this for x? Set them both equal to 0. So x minus 2 is equal to 0, or x plus 1 equals 0. X equals 2, x equals -1, and boom, we have 2 x-intercepts. So I like to use factored form when I'm finding the x-intercepts, and if you're like, I don't want to do that, it's okay, you'll eventually have to factor, because if I had used the original equation, I would have gotten x squared minus x minus 2 at this point equal to 0. And it's like, oh, how do I solve a quadratic for my x values? We would have to factor it. So it's a bit of a shortcut if you go straight to the factored form first, but if you don't remember that, you will eventually get there by knowing that that is how we solve the quadratic aspect of this. So let's go ahead and plunk those 2 points down. 2, 0, right here. -1, 0, right there. And those are our exact points. So now for typing this in on our calculator to figure out where our swooshes are. When you type this in, make sure you type in the original equation just in case you goofed somewhere with your factoring. Also, trap those trinomials and binomials in parentheses. So x squared minus x minus 2 in parentheses on the top, and then x squared minus 9 in parentheses on the bottom. Go ahead and type that in and see if we can sketch our graph. So, ooh, an interesting looking graph, isn't it? So I can get through these points exactly. Curving towards the asymptotes. And then I've got a swoosh up in this quadrant, sandwiched in between those asymptotes, and a swoosh in that quadrant. So folks, that's going to be it for notes for today. So what I would like you to do is go to your homework packet. And there are, how many problems of graphing? There are 9 problems of graphing. These are going to be due tomorrow night. We will be doing more practice in class tomorrow. But it's my recommendation that you try to get 1 through 4, maybe 1 through 5, done in class today. So the rest of the time is work time, so you can practice putting all of that stuff together.